right? I'm really going to try and explain this. See how this goes. All right, so look, we don't want to overcomplicate it, but let me focus first on this one, all right? I want you to look at this x squared, and what we're doing is we are taking the derivative of it, right? But we're treating x like the independent variable. This is critical that we're treating x like the independent variable. So when I do this, I want you to use the chain rule. Even though you don't have to, I want you to use a chain rule. You have something squared, right? So the derivative of that should be 2 times, that's something to the first power. Chain rule says now times the derivative of what? X with respect to x. So do you agree that the next part is the derivative of x with respect to x? Which is just 1, isn't it? We said the derivative of x is 1 a long time ago. So this does just turn out to be 2x times 1, which is just 2x. So that part, there's nothing new. But now let's look at how it works when you do it with the y squared. If I say take the derivative, of y squared, right? But I'm differentiating with respect to what? X. Do the chain rule again. I have something squared. Derivative of something squared is 2 times that something to the first power. Times. Now, you're taking the derivative of what? Y with respect to x. And so this next piece is dy dx, not 1 anymore. See, dx, the derivative of x with respect to x is 1. The derivative of y with respect to x is not 1. What is it? Well, that's what we're asked to find. The original problem said find dy dx, right? It just appeared. That's what I need to go figure out what it is, right? Make sense? Okay, so look, let's just work through this again, okay? This right here is going to turn into what? 2x. Okay, 2x plus, now this is 2y times dy dx, right? And then equals 0. And remember, the problem in the beginning, I said find dy dx, right? I said find dy dx, which I said, remember, is equal to y prime, right? I want to know what that is. Well, there it is. Isolate it. Get it by itself on one side of the equation now. So if you need to get this by itself, why don't we move that 2x over to the other side? Do you get this? This is critically important. I'm going to tell y'all a story in a little while. Okay, so I have 2x. Oh, wait, no, I was going to move that 2x to the other side, right? So I have 2y times dy dx equals negative 2x, right? So all I did there was just move the 2x to the other side, which made it negative. And if I want dy dx by itself now, I divide both sides by 2y. So I get dy dx equals negative 2x over 2y. The 2's will cancel, and you get dy dx equals negative x over y. There it is. Didn't I tell you that the derivative was going to have both the variables in it? Didn't I tell you it was going to have both the x and the y? There it is. There they are. Now, this is the thing that is just absolutely amazing about what we just did. I think it's amazing. Maybe you won't. Let's go back to the circle. This was x squared plus y squared equals 16, right? All right, let's go to this point right here. Do you know the point? Do you know that point on the circle? What's the actual x and y coordinate of that point? 0, 4, right? Because this is a radius 4. That's the point 0, 4. The tangent line is there, right? The slope of it is 0. That means that if I use that formula, I better get 0. So let's go ahead and replace x with 0 and y with 4. If that's 0 and that's 4, that's 0 over 4, which is 0, right? Okay, what would happen down here? 0, negative 4. You would also get a slope of 0, wouldn't you? What about here, though? That's the point 4, 0. What happens if you plug in 4 for x and 0 for y? 4 over 0 is undefined. And do you remember what the slope of a vertical line is? Undefined. Vertical lines don't have slopes. Their slopes are undefined. And the derivative formula is telling me that. What would the slope of the tangent line here be? What should it be right here? What should that slope be right there? If this was 45 degrees, okay, or pi over 4, 45 degrees. That should be a slope of negative 1, shouldn't it? How do I know it would be negative 1? Well, do you agree that if this is 45, the x and the y coordinates are exactly the same? So if I put the same x and y coordinates here, this would turn into a 1, but then it's negative. So it would be negative 1 there. What if I pick this point right here? Those would have not the same x and y coordinates, but they'd be the same numbers, right? One would be negative and one would be positive. So when you did the ratio of those two, you would get a negative 1. But then you make it negative again, and that's positive 1. And the slope of that tangent line is positive 1. So it works. You can do this for any curve. Any curve, no matter how crazy the curve is. As long as you can somehow isolate dy dx, you can find the slope of the tangent line, but you need to know the points. Okay, so you have to be able to find the points to do it. Should we do another one? Good. Let's see. Where is it? Let's do the second one. I just need to grab it real quick. Okay. All right, so now let's look at x cubed plus cosine y equals x plus y squared. Let's find dy dx. We have not been using the notation dy dx that often, haven't we? We haven't, right? And I told you that there were two people who came up with calculus, Leibniz and Newton. And Leibniz used this notation, Newton used a different notation. Leibniz notation is much easier to work with when it comes to implicit differentiation, because Leibniz notation stresses what the independent variable is and what the dependent variable is. And if you just write y prime, you are assuming that x is your independent variable. You don't see it anywhere in the notation. Right? So this is a better notation for what we're doing. All right, so I'm going to start this out. So what do I do to start this out? Just take the derivative with respect to x on both sides of this equation. On the left side, I have a sum, right? So I can do them individually again. I'll write it out. D dx. I know that on the homework solutions I don't write it out like this. I don't show as much detail. All right. What is the derivative with respect to x of x cubed? 3x squared. So it's just going to be your standard derivative, right? Okay, so this is going to be 3x squared. Does everyone realize that there really is a little dx sitting outside here that we don't need to write? Okay. Plus, now, What is the derivative with respect to x of cosine of y? Negative sine y. Negative sine y, that would take the derivative of cosine of something, right? Then you have to take the derivative of the y itself with respect to x. I'm doing chain rule here. So what is derivative of y with respect to x? dy dx. See, that dy dx has to come out somewhere. Somewhere in there it's going to have to come out, right? There it is. If you miss that step, you're not going to get your dy dx. So if you do your differentiation and you never see dy dx, something is wrong, right? Any questions on that step? Sure? Okay, derivative cosine of something is negative sine of that something. Times derivative, what was the something? Y. What's the derivative of y with respect to x? dy dx. Okay. Equals derivative of x with respect to x. 1. That's just like saying, hey, what's the derivative of x, right? Plus, now what? Derivative of y squared with respect to x. 2y dy dx. Ah, it popped out in 2 places, didn't it? Popped out in 2 places. Well, that's okay. That's all right. So here we go. I'm going to rewrite this. Just clean it up a little bit. 3x squared minus, I'm going to write it this way, dy dx sine y equals 1 plus 2y dy dx. The only thing I did there was eliminated the plus minus in parentheses and just made it a subtraction. And I put the dy dx in front of the sine y. We good with that? What am I trying to do now? Get dy dx by itself, right? Somehow get dy dx by itself. So the method to do this is as follows. You will take every term that has dy dx in it and get it on one side of the equation. Everything that does not have dy dx on the other side of the equation. Y'all hear me? So this one has a dy dx in it, and this is a positive term, isn't it? This has a dy dx in it, and it's a negative term. So I'm going to move this one to this side. I could have moved this one to that side, but I'm going to decide to move this one over here. Additionally, this does not have a dy dx, so I'm going to move it to the left side. And here's what I'll get. This becomes 3x squared, you tell me, 3x squared minus 1 equals, let's go 2y dy dx plus dy dx sine y. We have not solved for dy dx yet, right? Anyone have an idea of what I'm going to do next? Why I did that? What am I going to do? I'm going to factor out a dy dx. See, I know I have a dy dx in both of these terms because that's the way I move things around, right? I move them so that they both had dy dx and nothing else over here that, well, anything that didn't have dy dx I put over here. So now I'm going to do like a greatest common factor, like GCF from college algebra. I'm going to factor out dy dx. And what would that leave me if I pull that out? 2y plus sine y. And I am one step away from having the answer. This is multiplication. I will divide this, and that means divide it on this side and that side, and we're there. The left side is 3x squared minus 1 over, this got divided on both sides, 2y plus sine y equals dy dx. I now have a formula that will provide me with the slope of the tangent line to that curve, but you must provide me both an x and a y coordinate. You provide me an x and a y coordinate, and I will provide you what the slope of the tangent line is. Okay? Questions?
Yes.
Yes.
Is there always going to be the same amount of x's to the amount of y's? Or
What do you mean the same amount?
Because I noticed on the first one we did the circle, I had one X and one Y, and this one has.
No, that's just, yeah, no, there's no guarantee for anything like that. No. All right, I want to do the same problem here. That same exact problem. What was it again? I forgot. X cubed plus cosine y
equals
x plus y squared. I want to show you another way you can do this using a slightly different notation, all right? And if you don't like it, that's fine. You don't have to use this. You can stick with what I just did. But as time progresses, we try and get a little bit faster with this. So here's the way that I do it, that I've done this, I guess, in the past. You might see this on the homework solution videos. When I go to take my implicit differentiation, what I do is I draw like a squiggly. This is not an official mathematical symbol. That just, this is letting me know I'm about to take the derivative on both sides with respect to x. Okay? And I know it's with respect to x. I know right now y prime equals dy dx. I'm going into this problem with that understanding. Now watch what I do here. Derivative of this is 3x squared minus sine y times y prime equals 1 plus 2y times y prime. That's the exact same thing we just wrote out. It was derivative of this with respect to x, which is 3x squared. Derivative of cosine is negative sine. I already took care of that. Derivative of cosine of something is negative sine of it. But then derivative of what's inside, instead of calling it dy dx, I just call it y prime. And then over here, derivative of x is 1. Derivative of that is 2y, y prime. Same thing. And now I would isolate y prime. So I get all my y primes on one side. And that's the same work, right? That's the way a lot of times I will do it on the homework. Give you another example. The one x squared plus y squared equals 16. The problem we did this before this, I'd write 2x plus 2y, y prime equals 0. That would be my derivative. That would be my implicit differentiation. Derivative of this, derivative of that, derivative of that. You see it's the same thing? Sure? Okay. Let's do one more. Let's see how bad this last one was on the examples. If it's not appropriately bad, I'll give you something appropriately bad. No, this one's pretty good. It's not great, but it's pretty good. Cosine of xy equals 1 minus sine y. We want to find dy dx. I'm going to state that now. I need to state the instructions. Find dy dx. So let's start on the left side. I'm letting you know I'm taking my derivative, all right? What is the derivative of cosine of something? See this chain rule now. Cosine of something is negative sine of the something, right? So isn't this negative sine of x times y? Times, chain rule, times the derivative of what's inside, which is a product rule. Isn't that x times y? Isn't that multiplication there? This is multiplication. Which means that I need to do right here f prime g plus g prime f. With me? F prime g plus g prime f. So I'm going to do derivative of this times this plus derivative of this times this. What is derivative of x with respect to x? 1 times y plus, now what is derivative of y with respect to x? Y prime or dy dx. Times x. So this next piece, I'll stick with dy dx. Is that all right for now? Times x. That is the derivative of the left side. Questions? Clarification? Chain rule, right? This was chain rule. You had cosine of something. We didn't have addition this time. We had multiplication, so we had to apply the product rule, right? But we're done on the left. We've done the outer function and we've done the product rule. We're done. equals comes next. Now on the right side, you have two different terms separated by subtraction, so do them individually. Derivative of 1, 0. Derivative of negative sine of something. It's going to be negative cosine of whatever's there, right? What is there? Y. Times dy dx. Where did that dy dx come from? Chain rule, you had to take derivative of what was in here, which normally would be a 1 if that was an x, but it's not. It's dy dx. There's your derivative. I'll clean it up a little bit. Ooh. This is where things can get a little bit messy. Yeah. What am I doing? Okay. Okay, what did I do? What did I just do? I distributed negative sine of xy through to each of these. Why would I do that? Because I'm trying to get dy dx by itself on one side of the equation, right? And you cannot get this dy dx by itself on one side of the equation if it's trapped inside of this parentheses. You have to release it from the parentheses. And the only way to do that is to pass this through. So when I multiply this times this, the y just joins out here with the negative. When I multiply this times this, it becomes a minus. The x dy dx goes out in front of the sine xy. That fair? Now I can get anything that has dy dx in it and move it to one side. So these are the two pieces that have dy dx in them, right? Those are the two? So how about, which way do you want to move things? It does not matter to me. I do not care. Add what? You want to move this one over here? Okay. So if I move this one over here, that means it's minus here. It'll become plus over here, right? And that'll leave this guy by itself, which doesn't have a dy dx. That's good. And on the other side, both terms will have dy dx. All right. So I've got now negative y sine xy equals, when I moved that over, it became positive, didn't it? And so I'm going to put it first because it's positive. Before I forget, was it last Wednesday that I wasn't in my office after class? It was, right? My daughter is sick today, and I'm going to be in class. I'm going to be in my office after class probably for about 30 minutes, and then I've got to go pick her up, take her to the doctor. Dy dx, let me see, cosine y. I apologize, but can't control these things. Okay, any questions? Just move that over, right? The whole goal of that was to have two terms that have dy dx in them so I can factor out dy dx. There we go. So I pull out dy dx. When I pull it out of here, I'm left with an x sine xy. When I pull it out of here, I'm just left with that cosine y. And the final step, divide that out. This big ugly thing gets divided on both sides. Look, your answers are going to be ugly, okay? No one's promising you pretty answers here. But the answer will provide you with the slope of the tangent line so long as you provide me with the x and the y coordinate. There we go. All right, that's it. Give me x, give me y. Now, let me point something else out. You can't just plug any value of x and y in here. All right, the x and y that you plug in has to satisfy the original, I forgot the original problem. What was it? Cosine xy equals 1 minus sine y. So the only x's and y's that are actually valid here are x's and y's that solve this equation. So like I'll give you an example. Would the origin work here? Would 0, 0 work? Is that point here? Cosine of 0, right? Cosine of 0 is 1, and sine of 0 would be 0, 1. So that point lives on that curve, right? So you could plug 0, 0 in here, and you would get an answer. It looks like you get 0. Let me go back to that curve. Where was that picture? Wait, was it? Oh, that wasn't. Oh, we didn't do this one. Yeah, that's right. I never graphed it. Oh, well. Let's go to the Desmos, see what it does. So if I do cosine of x times y equals 1 minus sine y. Wow, look at that graph. Now check this out. Where was I checking? 0, 0. Is the slope of the tangent line there 0? Yes. There's another point up here, though. That looks like pi to me. Does pi work in here? This looks like the point. To me, it might be wrong here. This looks like 0 pi to me. Does 0 pi work here? What's sine of pi? 0. So if you plug pi in right here, you get sine of pi is 0. And then you'll get 1. And if you plug in 0 for x and pi for y here, it doesn't matter. That's still cosine of 0. So you're going to get 1 equals 1. So this is the point 0 pi. And if you plug that into that formula, which I've erased, the derivative, you should get another tangent line of 0 here. Look at this. This is not a function, obviously. It fails. Look at it. It fails a vertical line test like a bunch, right? But this is a graph. Now, why would you ever want to be able to do this? Well, look, think about the real world, all right? You're always talking, real world, right? Okay, when you think about like a real world application, let's say you take something as simple as, and this is really useless, but let's just think about, if I have an ant here, I don't know what an ant looks like, but there's my ant, okay? There's my little ant, and I'm just going to put him down on the floor. We're looking from the top, and we just say, start walking, right? This thing starts walking. I have no control over its path, right? So it starts walking along here, and it may turn back on itself, right? And it may do whatever it wants, right? I can't force this ant to live in an XY coordinate system and force his path to be a function that passes a vertical line test so that I can do calculus, right? I need to be able to allow the freedom of motion in all directions so that I can and still have a way of finding doing the calculus. So later on, this could be some sort of rocket that you just let go and it starts going, right? And it's got a path. And then what we're doing is we're finding this tangent, and we're able to find like the direction. Like if you cut off the rocket right there, where would it go, right? So it's like, shh, and then you turn off the engine. Where would it go? It would go in a path that would be in the straight line, tangent line, right? So you got to be able to do calculus for curves that are not functions. So that's what we're doing. And then imagine later, you extend this into three-dimensional space instead of a flat sheet of paper. That's what you do in Cal 3. You go into 3D, and now you have paths, three-dimensional paths.
Do you use it for model stuff?
Well, yeah, because then you start talking about vectors. You get into vectors, and you have tangent vectors instead of tangent lines. You have tangent vectors, and vectors have magnitude and direction. The length of the vector is basically the speed. So we just keep extending this until we finally get models that work in the real world. It's kind of like the example in college algebra of they give you a formula for objects that fall, and they say take out air. They say ignore air, right? And then you're like, well, why would we ever want to ignore air? Because if we put air in, that formula gets too complicated to work with. So that's the same thing here. We have to start out with a basic two-dimensional picture We start out with functions, and then we extend it. Now let's go into just general paths, and then we go out of 2D to 3D, and then you start adding more elements onto it, and eventually you get some ugly stuff that you look in an engineering book and you see this ugly thing. Well, you've now accounted for all these different things. Okay. All right. 10 minutes. Just want to show you this now. Same thing. X squared plus y squared equals 16. Find dx dy. What is going on here? We already did this problem?
Asking for dx dy.
I didn't ask you for dx dy. I asked you for dy dx before. What's the difference? Now y is your independent variable and x is depending on y. We are assuming that x depends on y. Now let's see how that changes things. If I go to take the derivative, I'll go a little more notation here. I'm differentiating with respect to y now instead of x. Right? Then when I take the derivative of this, I'm going to do them individually. Again, I'll write more notation out here for you. I'm just going to put 0 over here. The derivative of constant is still 0, all right? Doing these individually. Do you see the difference? What is the derivative of x squared? What's the derivative of x squared? 2x, so you're doing chain rule, 2x, but it is now not 1. It is what? dx dy. Because, look, you say, take derivative of something squared, the 2 comes out. Now take the derivative of x with respect to y. That means take the derivative of x with respect to y, which is no longer 1. Right? But that's what we're looking for. So it has appeared. Now over here, what's the derivative of y squared? That's just 2y. Because it's 2y dy dy. Because I'm differentiating with respect to y this time. So dy dy is 1. Understand the difference between those? Equals 0. And now you would solve for this, you move that over, and you get a formula. And you might be asking yourself, why would I need to solve for, why would I need to do this derivative as opposed to the previous one, right? Why do it this way? And that you're just going to have to wait for the next section. You'll see why we would want to do it different ways. We good? 7 minutes. Let me do one last example. Y equals 1 over x. Find y prime. This is a problem that you've seen in the past. Now, if I write y prime on the board or on a test, everyone may assume that I mean dy dx, okay? Unless I state otherwise, y prime means dy dx. All right? So is that an implicit or explicit equation? Explicit. You can solve for one of the variables. In fact, it is already solved for y, isn't it? So if you wanted to take derivative of this, you would just go back to the old school way of doing it, old school meaning last class, okay? And you just rewrite 1 over x as x to the negative 1. Bring it up, right? And then you use your power rule. So what would the derivative of this be? Y prime would be negative x to the negative 2, right? Negative 1 comes out. And this is really just negative 1 over x squared if we drop that x squared down. Did the quizzes get around to everyone? Is that packet still floating out there somewhere? Okay. Sign-in sheet is coming around. We'll start it back here. All right, so that's the derivative. We're done, right? Okay, that's it. I just want to show you that you could have done this with implicit differentiation. Let me show you how you could have done this. Couldn't you take this and rewrite this as xy equals 1? Multiplying both sides by x first. Yes? Okay. And now you could do the implicit differentiation here. And when you take the derivative of the left side, what will you have to do? Left side. I heard it. It's a product, right? It's a product rule. What's the derivative of that product? You have derivative of x times y plus derivative of y times x, right? What is derivative of x with respect to, I didn't say it, but I just told you, what do I mean by this? dy dx. So this derivative of x with respect to x is 1 times y plus derivative of y with respect to x, dy dx, I'm going to write as y prime times x. That's your product rule on the left. Equals derivative 1, 0, right? Y'all still good? Let's isolate y prime. So I'm going to move y over. So I get y prime x equals what? Negative y. Still good? Divide by x. Y prime equals negative y over x. Wait a minute. These don't look like the same answers, do they? But they are. Let's see why they are. Right? I'm going to show you now why these are the same answers. Go back to the original problem. What was y? What was y? Y was 1 over x, right? So isn't this the same as negative 1 over x over x? Right? Y is, well, negative y would be negative 1 over x. Then over x means you now divide and you reciprocate, and when you flip that up, what do you get? Negative 1 over x squared. So you get the same answer. So I'll tell you all this quick story. As the sign